Hello, everybody. I'm very proud to present you today an update on distributed acoustic sensing technologies from Febus Optics. So I'm Vincent, the technical manager, and I will present you the last developments on our DAS, the Febus A1R. So a brief introduction of the company. So we are a French manufacturer on distributed sensing solutions. We push very hard with our R&D to provide state-of-the-art solution through patented technologies. You can see on the map, we are present at several locations in the world, but our headquarters and main facilities are in France. We can provide full solutions as well as, let's say, bare DAS systems, the DAS systems alone. And we are focusing on the markets you can see below. So, since Thomas has brilliantly presented distributed generalities or generalities on distributed sensing technologies, I will be brief on that. Basically, when you do distributed sensing, you have a box. For us, it is the Febus A1 today, and you launch a pulse into a fiber optic cable, and then you use the light propagating backward here in green, backward to the instrument, and then you analyze the light. And you can see here, I don't know, do you see my cursor?
Yes, we do. Yes, yeah. We do.
So here you can see the different components from the light. So Raman component, Brilliant component, but here we will focus on Rayleigh scattering as Thomas presented brilliantly before. So at Febus Optics, we can manufacture 3 types of distributed sensing system: Brilliant DSTS, Raman DTS, and DAS, distributed acoustic sensing, for which I give my talk today. My colleague Pierre will give a nice talk tomorrow on DSTS and DTS. So let's focus on Febus A1, the DAS from Febus Optics. So here you can see a summary of the technical specifications from our interrogator. And let's focus on the red square. So we have a spatial resolution and a gauge length fully configurable by the user from 1 meter to 50 meter. We can have a range up to 50 kilometers. Then our instruments are qualified at very low frequency till 50 kilohertz, full bandwidth, with very low noise floor. And we can go down to 40 centimeters in terms of sampling. And we use standard output file format, HDF5, fully interpretable by standard, let's say, scientific software such as MATLAB or Python codes or any software. So you can see here a curve of the noise floor of the Febus A1R. It's in picostrain per square root of Hertz. You can see the y-axis, it's in dB, as well as the x-axis on the frequency. So here you have at a relatively high frequency, but we can produce the same curve at a lower frequency, much lower, because our equipment are fully characterized down to 10-3 Hertz, so 1 millihertz. And so here you can see the full characteristic of the Febus A1R at 10-3 Hertz. And you can see even artifacts here. It's because the lab is not perfect. Something like climate air is penetrating into the isolation box. So you have this small disturbance at between 10-2 and 10-1 Hertz. So another feature very interesting is that our gauge length is fully configurable during the measurement and after the acquisition. So my colleague, geophysicist Camille Jestin, will give a nice talk later today on that. So I won't focus on that. I would just like to highlight the importance of the gauge lengths, because you can see details with the good gauge lengths you cannot see with the wrong gauge lengths. So gauge length is a dramatically important parameter, and our device allow the user to change it even after acquisition, because the error is human. So we are working a lot with universities and academics. So because they like the way we can tune the data during the experiment and after the experiment. So here we can see a full screenshot of the Follow software, which is the interface, basic interface of the Febus A1R. So you can see here on the top, you can use filters provided by Febus Optics or custom Python filters to filter the data during real-time processing, or you can reuse the same interface to process them afterwards. So you can have, let's say, raw plot of the strain rate as a function of time and distance, but at the same time, you can plot FFT if you want, and at the same time, you can plot cross sections of the curve, spatially or frequentially. Beside this kind of scientific plots, you can have more industrial ones, such as the well-known waterfall view. This is an example of train tracking. So waterfall view is simple. You have the time, which is falling, and you have the distance here as the x-axis. So the time is falling and the curve is unrolled here, so you can see the train moving back and forth. So as we mentioned, we have we put a lot of effort on very low frequency measurement. So I will give you two plots. So this one is from a collaboration with GeoAsier, which is the University of Nice in France. So this is a measurement performed on a subsea cable, 40 kilometers long. And then you can see here the FFT of a signal, giving you, so frequency is in the x-axis, distance in y-axis, and you can see signal at lower than 1 Hertz, and we can go even further. So this is a measurement performed by the Stanford University, and it's performed on the Monterey Bay. And here you can see a plot on a subsea cable, 52 kilometer long subsea cable, and you can see the signal at 10-1 Hertz here, and we have been able to measure from the coast to the 52 kilometer length, and then we can see clearly the signals, the signal here up to 27 kilometers very clearly, and then the cable is diving into deep water, and then the signal is decreasing, but you can see no increase of the noise, meaning that the equipment is very, very well suited for the lowest frequency you have to reach. And then last but not least, this is an accessory we can provide to improve and to increase the range of our DAS measurements. So if you put our Febus A1 box and then you put 50 kilometers of fiber, so you're at the end of the range, let's say, and then we have developed this box, which is a REM for range extension module, or it's kind of repeater, if you want, in terms of signal. And then we can have a signal to reach another 50 kilometer, which is 100 kilometer in total. So here you can see the optical signal. So the same way Six I showed you before, you can enhance the signal here and recover 50 kilometers of range. And then you can see, you can recover a signal at 100 kilometer with a very, very small distortion. So this is a very powerful tool in order to increase the range of our DAS. It can be used alternatively or complementarily with enhanced fiber in order to reach greater distance with high attenuation or high optical losses. That's all for today. Thank you for your attention. And if you have any question, I'm here to answer. And you have my email for any further discussion you would want to have.
Thank you, Vincent. Very good. Interesting to use amplifiers on the way out. Do we have any questions? We're doing just fine on time. If there's any questions.
There's one question in the chat from Eileen.
Oh, there we go. Yep. You mentioned that.
I have to see the chat, so let me see.
I can read it for you, Vincent. You mentioned that the user can program their own filters with a comment about Python and VTK. Can you elaborate on how much flexibility a user has to design their own processing during acquisition? Specifically, is any processing software with a Python interface okay, or are there other restrictions?
There are no restrictions. There is a huge flexibility. The only restriction the user will face is the data processing has to be fast enough to be done real time. If it has to be real time processing, it has to be fast enough to be performed real time. Otherwise, the device will choose to skip some measurements in order to process the data. If the user wants to process the data afterwards, then there is no problem at all. But you have to know that Python/VTK program is quite touchy. So for let's say offline processing, the user may prefer using standard Python and opening the files than using filters directly on the software. It's much more for real-time processing.
Okay, thanks. And I'll just put two quick questions together. One was, how many repeaters do you think you can use in a row? So how many multiplexed? And then a question is, does the repeater require power?
Yes, I will answer before the last questions because it's the simplest. Yes, it needs power, but a few. It's like 10 to 15 watts per channel. We can use multiple channel repeater. There are several channels with several DAS or several DAS channels on the top. You don't have to program them. It means it's done before putting them remotely. So you only have to switch the power on, and then that's all. But it requires a very small power. Onshore, it's very suitable for with solar panel power supplies. And so first question. So first question was about how many repeater we can cascade, right? Mm-hmm. We already experienced 2, but let's say there is a trade-off to do, I think, between to be fully complete my answer, between using enhanced fiber, which has some advantages, and repeaters, which has another advantages. So because when you amplify, you can add noise, And you can as well, after a lot of repeaters, you will lose a part of the phase information because we are measuring phase, such as Silik Saga said. So I would say 2, but it depends on if you're on the configuration, losses, distances, and but in the lab, 2 is the maximum we have tested yet.
Good, thank you. There's one more question, but we'll catch that one later. We're running on a little over. Thank you, Vincent, very much. Appreciate it.
Yeah, thank you very much.
Okay, if we can bring up our next speaker is from Aragon Industries, and that will be Javier Vidal. So Javier, can you bring your presentation up?
Yeah, I will show now the screen.
Okay.
You are seeing it now?
We are seeing your screen. You're on.
Perfect. So, well, hello everyone. My name is Javier Vidal. I'm the product manager of the HDAS, the product distributed acoustic sensor of Aragon Photonics. In this fast presentation, I will just introduce us and our product. I will continue with the technology this product has itself, and then I will continue with some cases for the seismology field. That's why we are here. First of all, who are we? Well, we are a company located in Spain, concretely in Zaragoza. Since 2004, we have been manufacturing photonic test, measurement, and sensing equipments. Consider us as an innovative company because we have been exploiting out patents. We have really highly technical staff, and also we have been working internationally, let's say, with a lot of sales in more than 20 countries. And we have been constantly growing. Each day adding people to our crew, let's say. So we don't want to stop growing in this aspect. Why we are here? Well, it's because we have the HDAS, it's the product, and was the one we offer, let's say. The HDAS is named like this because we call it the high fidelity distributed acoustic sensor. Why we call it like that? Because mainly because it has a pretty high performance. We can reach up to 70 kilometers with 1 nanostrain sensitivity for 10-meter resolution. About the quality of the measurement, we say that they are really high fidelity because they don't have any kind of a distortion because they are linear and quantitative. We don't have any kind of fading points even for standard model fibers, the one that we use commonly. And also we have a homogeneous SNR, that means it's constant along distance. Also for scientific use and for users, we say that we are really open because the user can access to the raw data and to the instrument response and configure it depending on the concrete application or concrete measurement. And also we say that we are cost effective because we have certain advantages that I will comment later that are really due to the technology, and would allow us or the client, let's say, to have a less complex post-processing to apply in order to get better results. And it's a product that has been proven for seismic monitoring. That's why I'm going to show you now. But first of all, how did we get this until here? How did we arrive here with this product? All of this started with the University of Alcalá in Madrid with Miguel González, and we in the CSIC with Pedro Corredera, which are two of the maximum people controlling the seismic part in Spain. And both created Focus in 2011, Focus, a company related to the DAS technologies, where they perform a different test and measurement, and they ended in 2017 creating an HDAS prototype, which has related to patents related to the technology itself that I'm going to explain now, and also to our extent and how to extend the reach with other patents. On the other hand, as for our photonics, we started in 2004 with a USA, with a Brillouin optical spectrum analyzer, which is a really precise one with using the Brillouin effect. And then with the past of the years, we have been working a lot with our products, making them really solid, also entering in for example, in the solar field. And in 2018, we acquired Focus and this HDAS, and we also signed a contract with them in order to continue working on the DAS technologies. So in 2019, we ended up just launching the HDAS into the market. This HDAS, which has technology has, and why this is so special for us and so distinctive in terms of other technologies. What is called the chirp pulse phase OTDR. I will skip the part about how DAS work because my colleagues have already explained them perfectly. So our technology makes use of the other phase OTDRs. We send a pulse into the fiber and we see the backscatter light. In this case, our pulse is a little bit different because we perform a frequency sweep inside the pulse. That's why we paint it like in that changing color. So why we do that? Because in order to, for a given small change in the refractive index, in order to maintain the phase, in order to keep it, we need to change the frequency the same relative amount. So that means that, for example, if we apply a stimulus over a certain point of the fiber, and that affects into the refractive index of those points, that means a change in frequency that, as we had the pulse contained, let's say, in a certain time duration, we can transform that change in frequency in a delay in time. So to sum up, what we do is to transform the straight changes over the fiber into time delays. If we look at the interference pattern and if we look at the part of the fiber where a stimulus is being applied, we can see that that section of the fiber that is being lighted up by the pulse at that given time it has been delayed because of how we measure the changes. And what we do is to perform the correlation between those sections, let's say with the previous instant and the actual instant, and to get from there the strain rate. This allows us to achieve low sensitivity to low power sections give us the chance with the advantage that we don't have any kind of fading points. Also having this method of calculation patented. So thanks, as I said before, thanks to the technology, but not for any kind of post-processing that we will apply, we get some key features, key advantages thanks to the technology that are that the measurement is linear, which is shown here with just applying a concrete signal with a piezoelectric over the fiber and applying a sinus wave for a certain frequency and seeing that we maintain the shape of the signal and the frequency constantly. In the case of the DAS, in this case, it's an intensity phase OTDR. We have some harmonics and we lose the shape of the signal. It's true that we could apply some post-processing in order to improve the signal, but in the case of the HDAS, we already get that from how the technology is. Also, we have the key feature of being quantitative, which means that we can quantify the changes, which is, I think, is quite relevant in order to get meaningful information about the data we are acquiring, which is not the case in the case of the intensity phase OTDR. And also another key feature is that we have homogeneous, let's say, which means that the SNR is almost constant over the instance, and this is stable, which means, as I commented before, that we don't have fading points. All this technology has been used already for seismic application, also for other applications, but in this case I want to talk about the seismology. We have already seen that the DAS technology has certain advantages compared to the conventional seismometers. It is in the same case because we get a lot of synchronized channels, and from there we can really extract spatial and directional information. So by using the HDAS in terms of the seismic cases, let's say, I just want to point out two different cases, let's say. One for land optical fibers and the other one for the sea optical fibers. In this case, for the underground buried fiber, it was done by Caltech and University of Alcalá in Pasadena, using the fiber optical network of the city. And for the case of the submarine fiber, as Ethan Williams commented before. It was done in Belgium, making use of a submarine fiber of an offshore wind farm. It was also performed by these measurements by Marlinks. An anecdotic thing about these installations, let's say, is that in both cases they were able to detect an earthquake located in Fiji. I don't remember exactly the date, but they were able to detect at the same time the teleseism. For the case of the submarine fiber, I just wanted to remark that they ended publishing a Nature Communication journal with this title, and that you can search because it's public. And we participated the people of the University of Alcalá, and also the people have commented or already talked before, as Ethan Williams and so on. And in this case, they started much interesting information about with the fiber, let's say. Also detecting separating the different waves that you could detect by looking at the concrete frequency that each wave has, and also differentiating between the surface waves due to the different dispersion relation, as you can see in the graphic, between the ocean waves and the seismic waves. Also, they made a separation of current signals, which are the surface waves and the microseismic waves. This is much more technical information that you can look at into in the paper, but with much more detail, let's say. I just wanted to show you how they could use, and they did use the system for it. For example, how they managed to use this data to analyze how the ocean waves were moving along the day. How was the drift during the day? The other case, just for underground buried fiber, in this case, they also published they made use of the HDAS in Pasadena, in this case also for the Caltech and the University of Alcalá, and they ended using it in order to detect the different seismic vibrations for the vehicles. Also detecting the differentiating between the signal of the vehicles and then the urban activity, and defining and calculating more or less how the background noise was. In this case, it's really curious. Also, as my previous colleague has said, that they were analyzing the traffic lines and how they could evaluate that. In this case, they use this fiber for these reasons. And in this case, Caltech will use both the HDAS and OptaSense equipment there in Pasadena, which in what fiber at the same time. And this is an image of the HDAS in this paper. Where
just a couple of more minutes now.
Yeah, thank you. I just have a few slides and I'm ready. And then they were able to detect the different vehicles depending on the frequency band that they were analyzing. As you can see here, for example, how the traffic for the bands that they were analyzing were in this range of frequencies, and it's in this range the DAO, the trucks and the motorcycles and so on, and also how they could follow the vehicles and also detect the traffic congestion that they could happen in some points of the fiber. So this is more or less the two cases that I wanted to show you on how the HDAS was used in this case for seismic vibrations. Also, you can review more papers of the use of the HDAS and also this chill pulse phase of the technology that's related to the HDAS. For example, in this paper that you can search publicly, and you can ask me later if you want to access to it. And I just wanted to end to show you some clients that have already used the HDAS around the world, let's say, which you could contact for references and for questions also for how they use it. And also you can contact me to the email or to the web page if you want for more information, or you can even ask now some questions. So thank you for your time.
Thank you, Javier. Thank you very much. I think we will save, we're just right on schedule. So, and I'm not got any questions in the chat box right now, but if some do come up, we will come back to you. Thank you very much, Javier. Let's move on to our next speaker is Martin Karrenbach from OptaSense. Martin?
Yes, hello.
Yep, we can hear you.
Can you share the screen here?
And we are seeing your screen. Very good.
Great, yeah. Thank you very much for giving me the opportunity to update you a little bit on what we have been doing at OptaSense. And I'm just presenting here some of the results that many of my co-workers have actually been contributing to. OptaSense is a company that is pretty much integrated from manufacturing of lasers to producing DAS boxes to providing service. And we have a heavy focus on research and development besides the normal industrial applications. So we have a big research group, a basic research group in the UK. The more applied group is here in California in the US. And we are working with all the other offices in Canada, US, Dubai, and the UK to advance the system. So I'm not going to talk about the DAS system, the Rayleigh scattering, because so others have been doing it throughout the workshop. And the real ingredient here is at the left side of the picture, which is essentially the interrogator that many companies have different versions of, and depending how the modulation scheme works and the demodulation scheme works, you get different setups. But the main point is that you want to have a linear strain change mapped into a linear phase shift that you are acquiring here with the data. But we have seen a lot of examples in the past, and I go a little bit into the details of some of these boxes, but what we always would like is to have the optical signals to travel further, larger distances, so we can reach out 50 kilometers, 100 kilometers and beyond, have larger optical signal return back. It gives us a good signal to noise ratio, have a lower system noise floor, have high sensitivity and low frequency stability. And I'm trying to explain that a little bit in the next couple of slides. So if you look at the interrogator evolution, at least here at OptaSense, we started out in 2007 with somewhat first commercial CTEMPs boxes that allowed us to do DAS interrogation. And they were mostly aimed for pipeline measurements, security applications, long distance measurements of 40, 50 kilometers where you are trying to detect certain events, try to see what kind of activity is there along the fiber. That moved into the more energy application area around 2010, 2014, where a lot of the examples that have been shown this morning also on the time-lapse monitoring were proven in an offshore environment or onshore. And besides that, there are different specialized versions of interrogators that you can find. Some of them are tied to fluid flow monitoring for various aspects. Some are marinized versions that sit on the seafloor and acquire data there, and so on. But today I just want to focus a little bit on the updates that we did in 2019 and 20 with a new family of interrogators that are ODH5, ODH5X, and Plexus Quantix. And those allow us to reach further out with a finer spacing and a large aperture of measurements. On the right-hand side, you can see a little cartoon of signal frequency that the end user wants for maybe scientific measurements or industrial measurements. The measurement duration is on the left as the vertical axis. And most of the applications that we have heard about and we have been talking over the last years are on the upper right-hand side, from earthquakes to microseismic to seismic applications, seismological applications. But if we move down into the millihertz or microhertz range on long period measurements, there you can now look at subsidence, landslides, deformations, very, very slow creep type of applications, and casing deformation. So that's a very interesting aspect that has not stood out for quite some time. But if you're looking at that, you are looking also at temperature measurements, that you are that you need to do in order to compensate some of the strain and temperature combined effects of the fiber. And it's possible to do that with radius scattering type measurements if you do it in a certain combination. So the measurement, the sensitivity of your measurement is really governed by the fiber types, as we have heard a couple of times, but also the cable types, the packaging, the fiber arrangement, and geometry. And the interrogators mainly through the optical and hardware systems that allow you to modulate, demodulate, and enhance the signal that comes back. So in our case, we are able to use our sets of interrogators here with a variety of fibers. So we are not tying the interrogator to a particular fiber type that has been enhanced in a certain way, but it allows us to mix and match the different interrogators to whatever cable we can install or what we would want to use for the particular application on hand. And as you can see just from the diagram here, in terms of interrogator improvements, you can easily reach 10 to 20 dBs, while on the cable side, if you are playing with a fiber core or with the packaging itself to extract certain measurement physical quantities, you can reach another 30 dB in improvements. And just as an illustration, there's an enhanced backscatter fiber here in the middle that just easily shows you a 20 to 30 dB improvement just in the class itself. But the enhanced cable on the left-hand side, you can see that the packaging itself gives you a 10 to 20 dB improvement just without changing any of the class. So it's nice to have this toolbox of products available that you can mix and match together depending on what you would want to do. And if you compare the different noise floor levels on systems, this is just a rough diagram of those, and it shows for long fibers and short fibers some typical noise floor numbers that we get with different generations of these interrogators. It depends on the ping rate, the gauge length, and other parameters of measurements. But the main point is that if you have legacy and dark fiber installations where you really cannot change anything, the interrogator type is the only thing that you can change and that you can play with and improve. But if you have a dedicated installation, then interrogator types, fiber types, and cable types allow you to shift these noise flow curves down significantly to the extent that you can make extremely precise measurements for certain application areas. So if you have dedicated installation, which sometimes we do, then we can choose what fiber type and what cable type goes in there and how do we couple it. And here is a microseismic dedicated installation that uses just standard borehole fiber, but was cemented behind the casing in a fracturing environment. And here we are monitoring the microseismic emissions during the injection process. And in this case, there were 3 fibers active, one in a vertical borehole that just straddles the frac zone, then another 2 fibers active in 2 parallel horizontal fibers going all the way up to the surface wellhead. And in the middle slide, you can see the actual recording of such a microseismic event, very similar to what we saw this morning in some of the more detailed analysis. And I think we will see another one this afternoon. But this is the same event recorded on 2 horizontal fibers, and then that vertical snippet to the right is the vertical fiber. So you can see already from the PS difference that it gives you an estimate of the actual event distance and location. And if you invert these arrival time measurements, you can clearly find a precise 3D location in the frac zone of that event. So in this case, the microseismic event was actually fairly close to the frac stage. And we were measuring that a couple hundred meters, 300 to 500 meters away in those fiber wells. So in this case, this is a typical application of the standard interrogator, where we are measuring out with a maximum interrogation distance to about 5 kilometers. So these events are typically in between 1 and 3 kilometers away from the actual injection site. But what do you do if you don't have the choice of doing a dedicated installation? And there you have to overcome quite a bit of potential losses that are in there in the dark fiber scenario. So these optical losses come from fiber length and connectors. And on the right-hand side, you can see a very long lead-in of about 25 kilometers into the target zone all the way to the right, where we are really interested in measuring. And that would be typically a borehole going down another 5 kilometers. And on the top, you can see that fiber actually winds in and out of different boreholes along a stretch on the surface as well. And we do get full measurement, a high quality measurement after that long lead-in. But you can see that we already lost about 10 dB overall loss when we reached that sensing section. Now, this is a benign scenario, and if you want to have a higher sensitivity, you can also put some enhanced fiber into those end pieces. But in numerous applications on land and offshore, we really want to have the entire range of the fiber being measured. We want to have a dense array for high resolution for various applications, and not just focused on one particular analysis. So the region of interest is along the entire fiber. And in these long range type scenarios where you cannot choose the fiber type, cannot choose the length, and cannot choose how it was deployed, then your optical loss budget is really fixed. And you have to overcome that with your interrogator in the modulation systems and so on. That is really at the heart of this. But we can do that. And we can push out the interrogation range, keep the sensitivity, keep the resolution and bandwidth and the signal to noise ratio. And in the next couple of slides, I want to show you just one practical example of these measurements. Of course, all these things were tested in the lab very well before, calibrated, but with the CFOAM standard type measurement comparisons of noise floor and gauge length and all that. But it is important to go out in the field because you don't sometimes see the effects that are quite detrimental. In this case, this is a active source scatter that has been shot into a fiber that is about 1 kilometer down at the sea floor. So we have a water column of about 1 kilometer for the majority of that fiber. And only here to the left-hand side, we have a very quick rise over 2 kilometers to the shore station. And you can see that the signal here is dominated by just short wavelengths, near shore waves. If you filter that, you can see the actual seismic signal underneath, but typically it's a very rough sea there, and you have strong currents, strong changes in those patterns. But it's very nicely visible that in the middle section, you have a very clear view of the direct arrivals, the reflections, the scatterings, some guided waves, some converted waves. And very faint to the left and to the right, you can see those refractions popping in. So the direct arrival from the hydroacoustic wave is up here, directly above the source. And then you have your normal shot getter behavior out there. On the right-hand side, you see some long wavelengths, low speed sea waves and currents that come in from the offshore region. Again, this is not really filtered to improve any of the data, but just raw as it came out with a band pass applied.
Just a couple of more minutes, Martin.
Yeah, it's worth noting that the coupling here is the most unknown because the fiber lays directly on the sea floor. It's not being trenched, and that's a scenario that is very widely visible, very widely recognized really, because it's very expensive to trench those subsea cables in a very consistent manner that would make it useful for some of the seismological measurements. So you are stuck with what you have here, and some of the variations are these amplitude variations from sections to sections. But again, it's a very well behaved frequency response. You can go out from near shore shot out to midshore to the end of the interrogation distance. And you can see all those consistent behavior and signal to noise ratio for that. You look at common receiver gathers, you see that the air gun was really consistent all the way out. And this is just about 10 seconds worth of data here, but it shows clearly the reflections and the direct arrivals bouncing back from the lower regions. But just the last slide here is some of the fine scale measurements that you can do. And I grabbed out of an earthquake recording here the last 40, 50 kilometers of the data and focused in on the right-hand side on the last 100 meters or so. So with those one channel spacings, you really can see that some of the near seafloor variations have a profound impact, and you can track them even at this distance on that frequency scale if you are willing to look at the very fine scale variations. So these fine scales can be used for near seafloor and geohazard analysis, very similar to what was discussed earlier. That's important for various applications, but it can also be used for long-range sensing for aerial subsea coverage if you have a choice to put those cables in a 2D fashion. In this case, it was just a more or less linear array out to an offshore region about 120 kilometers. But the main point is there is no compromise necessary between the range and the channel density at this point in terms of what we can process in an interrogator, what can be modulated, demodulated, and we can keep the signal quality all the way out. You don't lose anything as you move it out. So we are looking forward in the early half of next year to about 100 kilometers on these dark legacy fibers. And I want to wrap it up with here because it's very useful for borehole applications, surface applications, seafloor, seismological applications. And at some point I stopped listing all the applications that you could do. But you want to keep your system open in terms of density of measurements and range and frequency content, and the DAS systems really allow you to do that. If you have some more detailed question, I'm happy to answer that and go also in details into some spec sheets of those interrogators that I didn't want to mention here.
Okay. Thank you, Martin. Thank you very much. I think we will keep moving. We're close to schedule, but thank you very much, Martin. I appreciate it. And we will have, again, if you have questions, put them in the chat box. We will have a little time at break. We can get some of these questions answered as we move forward. So thank you, Martin, very much. We'll move on to our next industry presenter. That's from Luna Industries, John Ohanian. And this will be a little bit different because some other types of measurements of strain. We thought we'd bring this in just to have some different, open up our eyes to other measurement techniques. So John, are you on? Are you muted, John? I saw you earlier. Did we lose him? I think we might have. Okay, well, I'm sorry. If we get him back on, we will move his slot up. What I think then we'll just do is we'll move on to our last presenter for this session, and we'll have a little bit of time at the end. That is from Terrasound Technologies, and that will be, sorry, I just had my notes up here. That will be Darren, Wolfe, and Brian Borkowski will be presenting. So if you guys can bring your slides up, I'm not sure who's first.
Hey guys, for those in the US, I'm standing between you and probably the end of the workday, and for those in the overseas, you and the end of the night. So I'll try to be quick through these. This is Brian Borkowski from Terrasound, and go ahead. So that's our team. Next slide.
Brian, just FYI, you are in presenter mode if you want to show your full presentation.
Oh, sure. Give me just a second to get that set up. My apologies.
No worries.
All right.
Thank you for that. So, you know, the highlight for me personally, I started this in 2009, working with the U.S. Army, putting it in places overseas, put it in multiple continents. Personally, did a lot of the operational side. Got out, started a company, and now we're really focusing on, even though we do have government clients, we're really focusing on commercial applications. Next one. Ours works, we are DAS, we don't do temperature, we don't do strain. We're all DAS, and again, really focused on the end user piece of it for commercial applications. Next slide. These are the three places that we predominantly play. We do flyer projects, we still do government projects, but kind of this is our commercial focus here. And I'll take a second to kind of talk about what we're doing in each one of those with you. So operational security, everything from border work to utilities work for security purposes. A lot of people, we've talked a lot about the head units. We've talked a lot where we tend to focus is the installation and the software. Those are kind of the two pieces we focus on greatly. We build a box in-house that's US government only, a coherent system. And then we actually get contract manufactured for us. The systems we install commercially, we put the software on top of them and do the installation and that type of stuff going forward. So for pipelines, we did the first, what I think is one of the first brownfield pipeline installs. I'm sure somebody else might have tried one too, but you don't hear a lot about these. So this is existing high pressure pipeline going through a tidal creek basin area in Virginia, which has very stringent digging considerations. We were able to install that, get it operational, and we've had a lot of success with that system. We've stopped 3 incursions on pipelines in just that one location in about a year, about 18 months. So that was a brownfield installation. We're moving to greenfield installations in the US with that same customer. Next slide. This one, traffic monitoring, what you're seeing here is the north-south road on the left-hand side is I-71 going through Columbus, Ohio, and the east-west is the I-670 corridor going out to the airport. What you've got is real-time northbound, southbound traffic flow data. In real time, anywhere there, we can tell you what speed something's going at the cursor point. With that, of course, we can find accidents, we can find potholes, all things like that. But that's just one of the operational things that we can give as a actual end user tool to the departments of transportation and stuff like that. So that's just an example of what we're doing there. Next slide. Here's a video. I'm going to let it run for it's a 2-minute video just to give you a general overview of kind of some of the stuff we're doing for our customers and how we explain it to customers. I know everyone uses DAS, so these are the points. For us, again, we're very focused on the software and the user experience for consumers. So it's not, we're trying to take it out of the scientific side and make it digestible for those customers. The images you're seeing here, we have a test facility in Southern Ohio that's 120 some acres. We have it fully instrumented with everything from cameras to weather stations to custom vaults for changing out fibers quickly. We can do about, I think, 13. That's one of the vaults in the top right, in the top center of the picture. That's a custom vault. We can do 13 different fibers side by side with a 1 meter spacing in between them. So we can use one source and get it across multiple different fibers to understand how it's reacting differently in those fibers. It's just a little example of mechanical digging, which we're going for our folks. And, we've got it down to this part here where we can tell the difference between not only fence climbing, but somebody's actually snipping your fence, right? Somebody's cutting it. Somebody's using climbing it, down to that level when we really get it down to the application for the users. This is another one on our test facility. Some more of the things that are there. The one thing I'd like to tell the academic community about the test facility, we do lots of government work, National Science Foundation, Department of Energy, DOD, DHS. If anybody would like to partner on any scientific things going forward, or if anybody is interested in borrowing and using our test facility for DAS research, we're pretty open to that. So send us a message and we can talk about that. Next one. Those are us. I got Darren, who's the director of our technology here, and Matt Wolfe, who's marketing and business development with us, and we're open to questions.
All right, thank you, Brian, and appreciate the offer of a test facility. That is quite useful.
Yeah, and that's a true offer. I mean, seriously, reach out to us, reach out to Matt, whoever. You know, we do a lot of science and technology work for the government in asymmetric technologies. Terrasound's kind of standing on its own, but we've got a lot of experience there too. So and past performance. So.
Okay, great, very good. Do we have any questions for the Terrasound folks? I guess maybe I would ask one question, which is related to how open source, you know, as the scientific side, you guys have developed your software. How open is that for use and kind of breaking into some of the boxes from some of us? That's what a lot of us like to do. Or is that something that's very proprietary from your side?
You know, it's varying degrees between our commercial and our government box. You know, I don't know what the makeup is. There could be a lease arrangement around something like that. You know, we obviously want to protect some of that stuff, but we understand that you got to get into it to use it. So I think that's a conversation case by case basis. We're not opposed to opening it up for the right folks with the right agreements in place.
Yeah, and I will throw in there that we do have a open API that we use for integration with different like tools, different sensor sets, et cetera. So that's obviously something that, you know, would be pretty easy to work with a coding-based person on.
Yeah, and I see Eileen's question there. Eileen, you know, potential, you know, what I'd like to say is detection is easy. Exact location becomes more difficult. Detection's a given. I mean, I can find that we have that now. Exact location, there are ways, if that's one of the threats at your location, that we can incorporate into the design to get you location. But exact location off of a single fiber is more difficult. It's not undoable. You know, we could, with our government box, we can do some pretty cool things. But our commercial versions, detection only is kind of what we tout. Right. And we can give you proximity as well. You know, we can tell you that was a really far off shot or that was so close.
Okay, thanks. I too picked up on the fact that there was a shooting range out there. Interesting.
Yeah.
All right.
We also used to have a tunnel there that's been closed for safety reasons because it's not running up. But we've got, you know, some of the other stuff. There's bridges, there's conduit over bridges, there's low water crossings, there's streams. I've got a mock substation there. I've got 4 different types of fencing. We've got all kinds of different scenarios to bring that through on that facility. So. A gas blowout rig, so all kinds of little stuff. So,
all right, thank you. Good. And I don't see any other questions. I'll just give John Ohanian one last shot if he is on. And again, I did do a quick check through our attendees. I don't see him, so I think we will save that presentation for our next workshop. And if there's no other questions coming from the audience from our industry folks, we'll take a little bit of a longer break than we might normally, but I want to thank all of you for participating and giving us updates on what's going on out in the real world.